Right, so so let me remind you what are the monkey and bananas problem. I think we can just turn this mode for now. So just first quickly remind you what were the domain formalization. So we define sort, which is a type. So the type and the objects. So T and F are the two objects that belong to the Boolean sort, and monkey and bananas and box are the objects that belong to this sort object. And there are three locations: L1, L2, L3. So this was what we said. Okay, it's kind of defining the universe. Okay, what are the types and what are the elements in that type? And then we define the state constraint, which determines the location of bananas depending on whether the monkey has the bananas, or the location of monkey depending on whether the monkey is on the box. So if monkey has the bananas, then monkey's location determines the location of bananas. Monkey is on the box, then box location determines the monkey. Okay? And we'll actually see later a question why this thing is actually important. The actions and preconditions are more or less straightforward. If we want to say action's effect, we write action in the body of the rule. If this action is true, then this becomes true at next time. So we have this timestamp t and t plus 1 that goes over the ranges over non-negative integers. So if work action is executed between time t and t plus 1, then at t plus 1 in the final time, location of monkey is at the destination L. It's pretty straightforward. Now, you can actually add more things on the body if we want to say more about the condition about this action. Okay? But for now, this is just simple thing. Just write action name on the body and the effects in the head. And we have a constraint that some combinations are not possible. That the monkey is at L and monkey walks to that same location L, this is not allowed. Okay? Same way, if monkey is on the box, so this T means true, then monkey cannot walk to any location L, because this L is a global variable that ranges over any location. And similarly, we talk about pushing the box, climb on, climb off, and grasp bananas. They all have the same structure. Okay? There are some other things, and I'm going to quiz you in a moment, but here is the point. Some actions we disallow. So walking to some location L at the same time pushing the box to the same location L. So when I use the variable L here, in the same rule, they refer to the same location L. Okay? If I use different L1, then it means it may be two different locations, so it could be also the same. Okay? Also, we don't allow monkey to walk and climb on at the same time, pushing the box and climb on at the same time, climb off and grasp bananas at the same time. Okay, so that's actually domain-dependent axioms, because this is kind of what you can change. Okay, you can actually allow certain combinations possible. You can add more actions and more effects, and you can disallow certain more preconditions. That's up to you. Now, once you have that, after that, we come across this domain-independent axioms, which is kind of universal across the different domains. So we say that fluents are initially exogenous. That's actually the rule that we will see again when we are doing the reduct. But basically we say this the cardinality bound. So you can choose exactly one value for each of the fluent. Now note here that sometimes you see the local variables are used there, and there are also global variables here. So if you look at this, Boolean is a local variable. So it says that at any moment, has bananas can be either true or false, but you should select exactly one. Okay? So when I write this one, this is just another way to write this one, because when you have local variable, this just expands inside the set. Okay, so global variable makes more rules, local variables just expands inside the set. So I could just write this way too, but I can also introduce this boolean as a sort and make a bit more succinct. Okay, same for the on box. So at initial time 0, on box can be either true or false. Okay, now the last one actually used both global variable and local variable. So what is a global variable in the last rule? O, right? O is a global variable because this variable occurs outside this set race. What is a local variable? It's at LL. Okay? So what it means is that you first ground all the global variables. So each of the objects, so object can be the monkey or bananas and box. So let's fix that O is a monkey. Then this rule will say for the monkey, there should be exactly one location associated with monkey at initial time. And same for the other objects. Right? Are we together? Okay, good. Now, this is actually another requirement, but I tend to differentiate between global variable and local variable by this naming convention. So if I use double characters here, that is a local. If not, then it is. But anyway, Klingo does not really distinguish this kind of thing. It's just for your own sake, that if you don't want to be confused, it may be a good idea to have some different notions, notations.
Zero and location indicate, sorry, LOC.
LOC is fluent. That says object O is at location LL at time 0. Okay? So unlike the previous two fluent, this is actually multi-valued because location can be multi-valued. It can be L1 or L2 or L3. Okay? All right. Now the next thing is actually very similar to this, but it actually prepend this thing in front. And the time is actually going from 1 to m. So except for the initial time, time 0, all the rest of the times we have to prepend this dash, arrow NOT. So basically, when you have this not some formula, this is actually basically same as double negation because this rule is understood as bottom if not f. They are actually this is equivalent to not f. So sometimes we put f here, like these formulas, and sometimes we use not f. And we actually did this kind of exercise before. Prepending double negation actually makes stable models be different. And we see another instance here today when we do problem 2, why this distinction is actually needed in the stable model semantics. Okay, so the next thing is actions are exogenous. It's also similar to the simple example that we discussed last time. So given the location L, you can either choose to walk to that location or not. And same for all the other actions. Okay? Now the time goes from 0 to n-1 because we think actions are executing between time t and t plus 1. So there are only 0 to n-1 transitions here. The next thing is common sense law of inertia. One way to read this is this choice works like a default. Okay, and we'll probably see why that is working as a default when you do the problem 1. But roughly the idea is you can read it as if monkey has the bananas, then monkey has bananas at time t plus 1 by default. Okay, and if didn't have, then doesn't have by default. Okay, same for on box and the location. Okay, so let's think about the state constraint. So we look at this rule that a monkey having the bananas determines the location of bananas, right? And we also look at this one. So let's think about this. So when the monkey walks to another location while it has the bananas, then bananas location also changes, right? So usually we can describe this in terms of this rule that if monkey walks to the location L, and if the monkey has the bananas in the previous state, then the next state location of bananas will be at the same location, same destination, right? Are we together? Now, this rule is actually redundant. We only described, if you remember what we did before, we only said monkey walks to another location, changes the location of the monkey. But we didn't say about the location of bananas when the monkey has the bananas. Why is this rule unnecessary? Yeah, Pam.
Because you're rule one.
Because, yeah, rule 1 is actually applying here. Now, the interesting thing is rule 1 doesn't say anything about actions. It's about state constraint. So for each state, whenever the monkey has the bananas, then the location of bananas are at the same location as the monkey, right? So what happens is you can only describe monkey's location change, and whatever that belongs to the monkey move together. But you don't have to describe this fact individually. This is known as the actual ramification problem. One thing that haunted also the people in AI some time ago is not as complicated, it's not as detrimental as frame problem, but it was probably second to that problem in terms of difficulty. So the problem was this. In this case, so the basic problem here can be described as how to describe indirect effects of an action. Now, monkey going walk to another location is a direct effect, but it also involves indirect effect if the monkey has the bananas. Okay. Now, why this is a problem? Because maybe if you think about maybe not monkey but me, I have carrying my microphone here, my shoes, and my wallet. Okay, my clothes, my socks, my shoes. Whenever I said I'm going to another location, I have to describe the changes in all my belongings, and that's actually infeasible to do. That's not very interesting thing, right? And there are a lot of axioms that you have to write to describe indirect effect. Okay, so this seems to be a difficult problem when you try to model this kind of reasoning about actions using some logic. In logic, you have to, unless you describe what happens there, you cannot derive any useful things. Okay, like Yale shooting problem. Okay, the problem is even if it is implicitly implicit understanding that humans have implicit understanding that the things do not change by default. Machines don't have that knowledge. What things do change by default, what things do not change by default, machines don't have this knowledge. And if you want to teach everything to machines, that's a very tedious thing to do. Same way here, ramification problem. If you're saying that everything that belongs to you also move, that is easy to do. But if you have to describe all of these effects of walking on individual belongings, that seems to be too much. Okay? Now, we don't go into the other formalisms, but there are many languages that don't have this kind of construct. And for that, it's actually difficult to describe this indirect effect. Okay? All right. So then, so this is called the ramification problem. Ramification or indirect effects of walking can be described by this rule. So let's move on. So before we show some rules, some actions cannot be executed concurrently, right? If you look, remember what was there. Okay. So these are the actions that we prohibit to be executed at the same time. Okay? All right. So let me actually ask you, actually let's start from this. Okay, so we didn't actually insert this. Okay, walking to location L and walking to location L1. So monkey cannot walk to two different locations. Okay, we didn't prohibit, or maybe we didn't explicitly stated this fact. Is this a problem? Shouldn't we say that the monkey cannot walk to two different locations? Pam?
I don't think you have to, because an object can only be at one location at one time. That was one of the.
Yes, that's true. There's another constraint saying that each object can belong to exactly one location for all the time, right? From the initial state to all the rest of time. So it actually does not make any difference. Let's suppose this is actually possible. What will happen? If monkey walks to location L and monkey walks to location L1, where L and L1 are different, so two different locations, then at the next time, it looks like stable model should say that monkey is at L and also at L1 at time t plus 1. But there is a constraint that this cannot be true. So this scenario is not possible. So this rule is actually redundant. Adding this rule does not hurt, of course, but it's actually redundant. Because the theory that you already you saw in the previous slide, it already entails this fact. Okay? So whenever the theory has a stable model, that stable model always satisfies this constraint. So you don't need to write this. Are we together? Okay. So a few more exercises. So why this is redundant? It's actually the same reason. Okay? So a monkey walks to location and pushing the box. That makes the monkey's location to be two different locations, but that is not allowed by the constraint. So this is okay. We don't need this. What about walk and climb off? So why this is redundant? So can monkey walk and climb off at the same time? If you want to climb off, what should be the precondition? Monkey should have been on the box, right? What is the precondition for walk? One of the preconditions for walk was monkey should not be on the box. So these two things cannot happen, no matter what, because their preconditions are different. They are negation to each other. So you will never see the state where on box and on box is both true and false. Okay? In other words, in order to execute the walk action, on box must be false. Monkey should not be on the box. In order to execute this, monkey should be on the box. Right? There is no state that has both on box to be true and false at the same time. So this concurrency will never happen. Okay? Right. What about this? It's the same. Okay? So precondition for grasp bananas is monkey should be on the box. So this is redundant. What about this? Same. Okay? Their preconditions cannot be true at the same time. So these are all redundant. Okay? All right, so that's some idea. And okay, I think that's a good time to stop here and talk about the problems. Okay, so problem 1, please come. So if you got confused about the redox, maybe you have forgot about how to form the redox, maybe it's a good idea to review that. And those presenters, when they post the solutions, study that carefully. That may help you understand these things. Okay, so let's actually continue the monkey and bananas. Okay, so now we have the description, and what do we do with this description? We want to do certain queries. One of the things is actually the planning query that we are talking about, how that the monkey can grasp bananas. Okay, so this is how you encode the planning problem. So note here that the planning is basically you're given the initial condition and initial state and the goal condition. Okay? So most in the classical planning, you give the full description about the initial state, and you give some conditions about the goal, what has to be true in the goal. Okay? If you remember the finite state machine, then this is exactly like that concept. Okay? You give the initial state, and you want to reach to the goal. Now the difference there is in finite state machine was accepting the string, but now here we want to find actions that leads to those goals. Okay, but the concept is actually very similar. So what did we put here? We are going to use only the constraint in this query. Okay, don't hear that. We are only looking at some paths that are allowed. Okay, so so it may generate multiple paths, but we will only look at the paths that satisfy the conditions. For that, we are going to use constraint forms only. Okay. All right. So, what is the initial condition? You just think about this as a double negation, which doesn't do any harm. But think about this as a constraint. What it says is monkeys is at L1 initially, bananas is at L2, and box is at L3, and the monkey does not have the bananas initially. Okay. So this is the initial state. Now, the final goal state is monkey should have the bananas. It's actually, this should be false and true. I don't know why. This may be a typo that I didn't update. Here, M is actually the maximum step. And this is what is a placeholder that the user can give. Okay, so this is a query that you can make. Actually, let's play with this. All right, so, oops. So this is the same program that you just saw. I just want to check whether I did. Okay, so this is actually the coding for the domain, and let's actually look at the planning. Okay, so this is a planning query that you just saw in the previous slide, and I did actually correct this to be F and T. Okay, so how do we execute this program? So what we do is to ask Klingo to find the plan. So here there was two files, monkey and planning, because I can change the query in different ways. I need to say what is the maximum step that we are looking at. So can monkey grasp bananas in one step? It's actually not possible. Can it do in this 2 step? It's also not possible. Can it do in 3 steps? No possible. Can it do in 4 steps? Yes. So that define these things. Now these are actually too much to read. So maybe okay. Let me actually comment this. So uncomment this. So we are going to only show the actions. Okay, that might be easy to read. Okay, so this is now the solution. So monkey, so this is time 0. Monkey walks to L3, and pushing the box to L2, and climb on at time 2, and grasp bananas at 3. Then at time 4, the monkey has the bananas. Okay, so this is how you execute the planning query. Any question up to this part? Okay. So the next one is prediction query. So here, everything about the transition system is about the reasoning about path. Okay, so in the planning problem, you are given the initial state and you want to reach certain goals. Now in the prediction problem, what you have is you know the initial state and you know what actions are executed. And you want to find out what is the resulting state about. So you want to predict what will happen if monkeys does certain actions. Okay? So let's look at a simple example here. So initially the monkey is at L1, bananas at L2, the box is at L3. The monkey walks to L3, then push the box to L2. Does it follow, is it entail that the box, bananas and the box are at the same location? Commonsensically, this is true, but how can we run Klingo to verify this claim? So this question can be actually formalized as follows. Determine the monkey and bananas domain when m equals 2, which I'm going to say mb2, conjoined with the negation of conclusion has no stable models. Okay, let's say this way. So mb2 is actually the full domain description. Okay. Now the query that we want to answer is whether this is actually the query. If this situation is true, then will the bananas and the box at the same location at time 2? So we want to check this claim. MB2 entails this query. But instead of that, what I can do is if you negate it, and this has no stable model. Remember this? We did this a long time ago, okay? So it was about the propositional logic, but the same concept applies to the stable model semantics. So what we are going to do is to formalize this way. So in the prediction query, same as before, you give the conditions that you know. And here it's not only about the initial state. So initially, of course, these are the locations of the objects. But we also say monkey walks to L3, and then monkey push the box to L2. And then we have to say that they are at the same destination. Okay? Now, if you negate it, what happens is they are not at the same destination, which means that they can be at two different locations. You can represent this in many different ways, but here is one way that I did. So we are counting the number of locations that the monkey and bananas are there. Okay? So if this is not 1, okay, then this is actually the negation of that conclusion. Let me say this way. If you only look at this one, okay, you count the positions of this object, and it's 1. That means they are at the same location, right? And if you put this one in front, that means they are not in the same location. So this is a negation of the query that you give. And if you call the Klingo, then Klingo will say no. There is no stable model. And that's a way that you check this prediction query. Okay? Let me actually show you what happens here. So here we need only 2, so we get unsatisfiable. There's no stable model, which means that the MB2 entails the query. Now you can actually do it in a different ways too. Let's actually change the prediction query. Let's actually comment out this. And instead of checking the unsatisfiability, I'm going to enumerate all stable models. And actually there are only 2. Actually, let me uncomment this. Let me add location because previously it was not showing the location. So you can try to generate all stable models, and it happens to be the only one stable model here, and check whether the bananas and box are at 2 different locations in all stable models. Okay, that's another way to do it. And here it's actually easy to check the location of bananas at 2. What is the so location of bananas at 2 is L2, right? And location of box at L2 at time 2. Yeah, location of box at time 2 is also L2. So they're in the same location. Now this way, could be actually a bit more challenging if you have multiple stable models. For each of the stable model, we have to check whether these two objects are in the same location. Okay, but they're actually equivalent. You can check that for all the stable models of this satisfies security, just like what I showed you, or you can check this way. Okay, they're equivalent. All right, the next one is postdiction query. Here, what it means is it's about the reasoning about past, while the prediction was reasoning about the future. So what we mean by this is you already know what happened as an actions, right? Some actions happened, and you are in the resulting state. You know the resulting state, but you don't know the initial state. So can you infer what was the case for the initial state? Here's an example. The monkey walked to location L3 and then pushed the box. Okay? Does it follow that the box was initially at L3? It is, because if the box was not at L3, then monkey cannot push the box. There was a precondition about pushing the box. So how do we model this? Here, this is something that we know. Okay? So note here that in the question, monkey walks to L3 and then push the box. It didn't say which location that the monkey pushed the box. So for that, I actually use the local variable. There's some location LL that the monkey pushed the box. Okay? And want to find out whether the box was initially L3. So this is the query. Okay, this is query, and we put the negation of the query. And then call Klingo to check that there's no stable model. Okay? Question? All right, so then it's your turn as a homework. So I'm going to ask you to do these two problems, okay, in addition to, of course, other problems. Here, you have to formalize these problems in the same way that I just described, okay, and check the claim using Klingo. So here's the knowledge that you have to represent. So problem 5, walking always changes the location of the monkey, but never changes the location of the box. Now, obviously, this is true. How can you check this? So in order to check this claim, you only need 2 timestamps, time 0 and time 1. Okay? But all transitions that you can consider, if every transition that has walking, the location will always change. In every transition that walking is there, box will never change its location. That's what you have to check. Problem 6, if the location of the monkey changes, then he either walked or pushed the box. Okay? So monkey cannot teletransport. Okay? So it has to do this action. So unless there's a cause for this, monkey cannot change the location. Okay? You have to also check this claim. So the hint is same as before. You just formalize this domain in terms of query. And for the internal checking, you have to negate the conclusion and check whether Klingo returns no stable model. Okay? All right, I think that's it. And the next class, we'll actually talk about Bloxwald and some other transitions. We want to spend some time on the basics so that when you go into the other things, I'm going to give more examples just to give you more confidence in writing this description. But in terms of theory, you already know everything. Okay, so you can start working on homework problems. Any question?